This video is going to be a brief introduction to some of the background knowledge that you should have for an organic chemistry course. And so this will be looking at a college 200 level, sophomore level, beginning organic chemistry. And so I'm going to be following my textbook that I had for organic chemistry over a decade ago, which is Organic Chemistry, and this is the seventh edition, and it's by L.G. Wade Jr. And so, like I said, in this video, I'm just going to go through a few preliminaries that you need to be familiar with going forward throughout the rest of this video series. And so, organic chemistry is chemistry that's focused on the study of molecules made with carbon atoms. And so that seems, if that seems very sort of narrowly focused, it is kind of, it's narrowly focused version of chemistry, but the carbon atom is so versatile that it needs its sort of own branch of chemistry in order to study it. And so the reason that it's versatile is just because of the way that the atoms for it are made up. And so carbon is atomic number, which means it has 6 protons. And so its atomic number is 6. Its average molar mass is 12.0107. And so the sort of the molar mass, if you remember from your general chemistry, sort of takes into consideration all the different isotopes of it, which is why for something like carbon, it's slightly over what you would expect for something that always has 6 protons and 6 neutrons. So you can get things like carbon 13 and carbon 14, which has more neutrons. But this is chemically where the carbon atom becomes a lot more interesting and more versatile. It has these 4 lone valence electrons. So that's what I have shown here and here, where we have these 4 unpaired electrons here on the carbon. And so the carbon can form many different bonds to a lot of other different atoms. And what we'll see in organic chemistry is the atoms that we will be mostly dealing with are other carbons, hydrogens, nitrogen, oxygen, and then the things like fluorine, chlorine, bromine, and iodine. And so those are things we will also see occasionally sulfur and even phosphorus. But so we'll get into that later, but the idea here is that the carbon can form many different bonds to these other atoms, and you can sort of piece them together in longer and longer and larger molecules. And so that's kind of what I have shown here. So this is just the way the carbon will bond with 4 hydrogens, where the hydrogens bring their own single electron to bear, and the carbon brings its single electrons to bear. And so you can end up with something like this, but we can also see that we could just keep building carbons onto it, because if we're bringing these single electrons to bear and the carbons bring these single electrons, then you can just keep building carbons and carbons onto it, and we could see that we could actually branch carbons off of it too, off of this linear structure here. And so what I'm going to show here for a little bit is just some of these carbon chains and sort of the way that we portray these, or the sort of conventions for actually displaying them. And so, especially in this early level organic chemistry, a big part of it is that you will just have to be learning the conventions of organic chemistry. And this is something that I've noticed with students that I tutor can kind of get tripped up on, because sometimes it can seem a little bit arbitrary, but there is good reasoning for it. It's supposed to be the most sort of intuitive way to actually think about it, but when it comes down to it, when you get sort of down to the base level, it's just convention. It's at some point in history, some chemist said this is the way that we're going to draw these things, and That's just how it's done. But anyway, so this is a 6 carbon molecule here. And so these are 4 different ways that you might encounter this drawn. And so we see we have 1, 2, 3, 4, 5, 6. And I'll get into naming in the next video. But this, because it's 6, would be called a hexane. Then you will also see it looking like this. This is more like the Lewis dot structures that you probably encountered quite often in general chemistry. You'll often see it looking like this. Sometimes these things will be bent like this at these 45-degree angles. Sometimes you'll see it as just a straight line. But probably the one that you're going to have to get used to the most is this one right here. So this way of drawing these molecules. And so again, it comes down to convention. So, I mean, the reason for the convention is that this is just a lot easier to draw. It's very fast, it's less crowded looking. And so it takes some getting used to, but once you get used to it, then you will come to appreciate the sort of, I guess, time-saving device that drawing it like this is. And so the thing to keep in mind, and this is something I'm going to remind you throughout, is that the way that carbon exists, so we were looking up here, the carbon can never have more than 4 things bound to it. I think there are some very extreme particular conditions where you can get more than that, but at this level and at pretty much most levels of organic chemistry, it will be maximum of 4 things bound to it, and the carbon, unless it's charged, will almost always have 4 bonds, even if they are in double bonds or triple bonds, but it will always have 4 bonds. So unless it's charged. And we'll see later on in this series that you can also have free radicals that are not charged, that do not have 4 bonds, but that's sort of a special case that we will discuss when we get to it. But for our purposes at this point in this, if you see a carbon in a molecule that doesn't have 4 charges, then it has to have 4 bonds. So when you see a drawing like this, so every point on here, so every sort of corner is a carbon. And so if you don't see any oxygens or nitrogens or anything onto it, you just assume that the bonds that are not to other carbons go to hydrogens. And so here at this end right here, this has only a bond going to another carbon, so it would have 3 hydrogens, which is what we see here. It's what we see right here, and it's what we see right here. Then this carbon right here, which is bound to 2 other carbons, must therefore have 2 implied hydrogens bound to it. And so that is indeed what we see right here. It's what we see right here, and it's what we see right here. And so on and so forth. And again, I will be sort of going through this again and again as we go through this material, but getting used to this way of portraying these molecules it's just something you have to get used to, because you will see it throughout. From this point on, when you're doing organic chemistry or biochemistry, that is the way that you will see carbon chains drawn. And so it's a space saver and a time saver compared to these other ways of portraying it. You do still see, like this one, for instance, quite often, but this one is the one that you will start encountering the most as we go through these organic chemistry topics here. And so this is just looking at it for another molecule. And so we see that we have this up here. And again, this comes down to convention, the way that this is written out here. And so we see that that we have this carbon right here, which is our CH3. Then this carbon here will be just the CH. And we know that because it's bound to 1, 2, and 3 other carbons there. And so this has to have sort of an implied hydrogen on it, on this carbon here. So it's a CH. And then you'll see this CH3 here in parentheses, and so that's talking about this substituent right here. And so that's in parentheses is telling you that it's a substituent because it's not part of the main chain, so that's why it's in parentheses. And we have our CH2, which will be this carbon right here. Then this CH will be that carbon right there. So we see we have in parentheses this substituent, so we go up to this CH, which is that one right there. Then these two CH3s, which are that one and that one right there. Then we have the CH2, and so that is that one right there. Then this CH3, which is that one right there. And so you can see that a little bit more explicitly in that drawing right there. And so we have this again, which is just the same as this above one, but now I've added this double bond right here. And so what you'll see different in up here, so we have this CH right here, which is this carbon right there. But then on here, so this has a bond going to that carbon, has a bond going to that carbon, and a double bond going to that carbon. So that's our 1, 2, 3, and 4 bonds. And so this carbon has no other hydrogens bound to it. This CH is the previous one. So we see this as 1, 2, and 3. So it has an implied hydrogen on it. And so that's why we have the CH here. Then this C does not have a hydrogen bound to it, and we still have these substituents right here. And so we will get the same thing when we are looking at other things other than sort of hydrocarbon substituents. So we have this NH2 up here, which is that substituent, this CO right here, because this carbon we see as 1, 2, 3, 4 bonds to it. So that carbon right there does not have any hydrogens to it. Then we have this CO here. So this CO, because we know that this carbon has to have 4 bonds to it, we know that this oxygen here is going to be double bound to that carbon because we are not seeing any other hydrogens bound to it. Whereas if we go to this next carbon here, we do see we have a CH, and we have this OH in parentheses, which tells us that we have this implied hydrogen here, and then a single bond to this OH right here. And so again, this right here is just sort of convention. So, you know, like why not put this oxygen here in parentheses? And, you know, like I said, it's just convention. So because we know, again, and a lot of these conventions come down to this. Because we know that carbon cannot have more than 4 bonds, we know that this carbon not having any hydrogens must be double bound to this oxygen right here. And so that's sort of how you know that that oxygen there is a substituent, how you know it's double bound to that carbon, and so that's how you know that it's not part of the main chain, how you know it's not sort of in between this carbon and this carbon right here. And so again, that's one of those things you kind of have to get used to, and in a way it kind of actually demonstrates why this this sort of way of portraying it is somewhat superior, because in this way of portraying it, you can actually see what is bound to what kind of bond it is, whether it's a single or double bond, where up here there is a little bit of interpretation you have to do. And so if you're taking an organic chemistry class, probably early on in the first semester, one of the things you're going to find in your homework is sort of translating between these two ways of showing these molecules. It'll give you this and tell you to draw this, or it'll give you this and tell you to write out this. And so that's just getting you used to using these different ways of portraying these molecules, and you know, sort of it's getting you used to the conventions that you will be seeing throughout your organic chemistry and beyond. So again, this is very similar. The main thing I wanted to show is that in this way of drawing it, there is 2 ways of portraying this carboxylic acid here. And so you'll see the COOH, which is this right here, where we see it has a single carbon, two oxygens, and a hydrogen, but you'll also see it as CO2H like this. And so those are two ways that you'll see it written this way, but you'll always see it drawn kind of like this. Another thing to know here though too is that whether this double bond is here and we have the single bond of the OH here, or you flip those around, doesn't actually matter, and that actually has to do with, well, it has to do with resonance structures, but it also has to do with the fact that there is freedom to rotate around that bond right there. All right, and so kind of switching gears a little bit here, another thing you'll need to be aware of, and you should have covered this in your general chemistry class, is this idea of hybridization. And so we have what we'll see on carbons in particular is sp3, sp2, and sp hybridization, where sp3 is when our carbon is bound to four other things, sp2 when it's bound to three, and sp when it's bound to two other things. And so the sp3 is bringing the s and all of these p orbitals here into these hybrid orbitals that we see right here, where the s is just bringing these, the s and two of the p orbitals here like that, and then the sp is just bringing an s, the s, and one of the p orbitals into it like this. And so knowing the sp3, sp2, and sp is important. So one way that I remember it is so sp3, like I said, is bound to four different things. So you can think of s, and then we have the p here, and our s has sort of an implied 1 up here, where the p has a 3 here. And so our 1 plus 3 is 4, and so that tells you that four things are bound to it. Where with the sp, we have s and p, this has this implied 1, this has 2. When we add them together, we get 3, and so that tells you that we are bound to 3 things. And then same for the s and p, this is an implied 1, this is an implied 1. We add those together, we get 2. So it can bind to 2 different things. And so that is sort of the way that I keep track of that in my mind. And so, I mean, that's sort of where these things come from, because we're bringing together 1s and 3p here. So that's why we have 1s and 3p here. But that's sort of the way you can think of how many things are bound to the carbon if it's an sp3, an sp2, or an sp. So another thing to remember from our general chemistry is these pi bonds, and so this is what we'll see in double bonds. So we have these 2pz orbitals, which is what we have in the carbon here, and so these will interact with each other because they are sort of well, they're parallel to each other, and they are perpendicular to sort of the plane of this molecule. And so they interact with each other and form these lobes above and below the molecule. And so it kind of looks like this when you see it drawn schematically. And so that is our pi bonds. So we'll also encounter triple bonds, and that will just have another pi bond sort of coming in and out of the screen on this portrayal right here. All right, so another thing to remember, and again, you've probably covered this a little bit in your general chemistry, is this idea of resonance. And so this is very important in organic chemistry because a lot of these molecules we'll be working with can have quite a few different resonance structures. And so remember resonance, so we have this this lone pair on this carbon right here. And so remember it's charged right here. And so that means it will only have a single hydrogen, and then it's bound to these two carbons. So it has three bonds, and then this lone pair here. And so this lone pair is going to collapse down onto this bond right here. Then this double bond will generate a lone pair on this carbon right here. And so we have this right there with this double bond right there. And kind of the thing to keep in the back of your mind when using these resonance structures, which we will use because they're helpful, is the reason that we use them, even though they're not strictly speaking accurate portrayals of what these molecules actually look like. And so that's kind of the thing to keep in the back of your mind is that it's actually in a sort of quantum mechanical mix of the two states. And so that's kind of what I'm trying to portray here, where we have sort of a partial double bond and partial double bond character right here, and this negative charge is sort of, spread between all of these three atoms here. And so we can see why this would happen is because spreading this charge out between multiple different atoms is helping to stabilize the charge on the molecule. And so that's actually a much more stable way for the molecule to exist. Like I said, throughout the course, we're going to be using these resonance structures because we'll see that, we can bond to things from this carbon atom, or we can bond to things from this carbon atom, and different things can adjust the rate at which it bonds. We react with one carbon over the other and things like that. But sort of, like I said, keep in the back of your mind that this is just sort of a useful tool for us in organic chemistry, in that quantum mechanically speaking, the charge is sort of spread between multiple atoms. But anyway, I'm going to go through a few of these here just as kind of an exercise. And again, very early on in the semester, if you're taking an organic chemistry class, you will probably encounter these kinds of things on your homework. So these kinds of exercises. And so we have this first molecule here. So we have this lone pair right here. And so that's going to collapse down on there, which will form a double bond from this carbon to that carbon. And then this double bond, the electrons will go up to that oxygen. And so we see here we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So here you're also going to see why I like to use these nice schematics here rather than drawing everything out, because my drawing ability is not the greatest. But anyway, you have 1 carbon, 2, 3, 4, 5, 6, 7, 8. And so this oxygen is on this third one here. So now we have a single bond to it because that the electrons from that double bond went up to that oxygen, and now we have a double bond right there. Let me see if I can draw that at least a little bit better. And we do have a negative charge on that oxygen. So we had the negative charge right here, and now let's move to the oxygen. So one thing to keep in mind when you are doing these resonance structures, so there are two sort of necessary but not sufficient rules for these. So one of them is that the charge of the entire molecule has to remain the same. So the overall charge of the molecule has to stay the same. So this overall charge on this one here was negative, and on here it is also negative. It's just moved to a different atom on the molecule. And the other thing that that has to be true of these resonance structures is that you are not moving any atoms around within the molecule. So, like if we have these hydrogens on here, you couldn't do something that would cause that hydrogen to move over there or something. So the sort of position of atoms within the molecule cannot change in the resonance structures. So those are sort of the two necessary but not sufficient rules for our resonance structures, that the overall charge has to remain the same, and the overall way that the atoms are sort of located in the molecule have to remain the same. All right, so this is another one, and this is just going to be very similar to what we had above, but now instead of this charged carbon here, this carboanion right here, we have a lone pair on this nitrogen, which is going to collapse down there. Again, the electrons from that double bond are going to go up onto the oxygen. So we have 1, 2, 3, 4, 5, 6, 7, 8. I guess I also put this up here, this double bond over here. And so the reason I put that there is as kind of a red herring. And I also have it on this one here, which is what reminded me to say. But it's true on both of these. I put that as a red herring because a lot of times you'll see that double bond and you might think, oh, these electrons here can collapse down and maybe, something happens over here that can cause these to go up onto that carbon, but that is not true. So this double bond is too far away from our lone pair here. And so that cannot actually happen. So this double bond will not actually be part of our resonance structure. That's the same. The same is true on this one down here. That one I put there as kind of a red herring. But anyway, again, we have our single bond to the oxygen here, which will have the charge, and now so this should actually be a nitrogen right there, and it's a double bond. And now what we'll see, because this has a hydrogen on it, this is actually positively charged. And so what we see on this right here, this molecule right here, has no formal charge. So it is not charged. It's a neutral molecule. This one, we have introduced some charges on it, but this negative right here will cancel out with that positive. So the overall charge of that molecule is neutral. And so this is something, this is another one of those things just sort of showing that rule I was talking about. The overall charge has to remain the same, but you can introduce charges as long as they cancel each other out to a point where the overall charge is not actually changing on the molecule. So then we have this, and this is another way we can see our resonance is if we have a positive. So we have a carbocation over here now. So the electrons from this double bond can actually move over here. So we have 1, 2, 3, 4, 5, 6 carbons. So we'll go 1, 2, 3, 4, 5, 6. And now our positive charge has moved over there, and our double bond has moved over there. And again, we see that the overall charge remains the same. The overall charge on both of these is positive. All right, and so then we come to this, and now we see that we can actually have multiple resonance structures, or more than two anyway. So we can have this collapse down here. This moves up onto there. So now we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So now we have this as a double bond. We have this as a double bond, and now we have the lone pair with the charge right there. But now we can have this collapse down on there and this go up onto there. And so we can draw this again. So I'm going to move this over here. And so we have 1, 2, 3, 4, 5, 6, 7, 8. Now we have the lone pair there with the charge. We have a double bond there and a double bond there. And so those are the three resonance structures for that molecule. So we can go down here, and what we see, we now have two charges on here. Uh, and so this can collapse down on there. This goes up there to generate our lone pair. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And so we have over here, so we can draw this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so now we have, so this is on the third carbon over, so that's the double bond there, and this now has the charge on it. We have this double bond there and that charge there. This will collapse down, that will go up there. And so now we have a third resonance structure. So we go like this. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we have this positive charge there. We have that negative charge there, this double bond right there, that double bond right there. And so then we will see this collapse down here. And so we will end up with yet another resonance structure here. And what we'll find is that now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have a double bond there, there, and there. And so these are all overall neutral, but what we see is that because this doesn't have charges on any of the atoms, this is actually going to be the major contributor. And so what we mean by that is that the molecule is going to be sort of in this form most of the time. And in fact, these forms here are going to be very minor contributors to this molecule, to the point that we would probably not even call this a resonance structure. So the reason I put this here is, one, to introduce this idea of major contributors, but two, you will probably encounter something like this in homework problems early on in organic chemistry class. But anyway, like I said, this is going to be the major contributor to this resonance structure. So the next one we have is here, and so this is just to show that this oxygen can be in the resonance structure. So we collapse that down there. So we have 1, 2, 3, 4, 5, 6. So we have 1, 2, 3. Then we're going down to this oxygen. Then 5, 6. And now we have this double bond here. So the positive charge is going to move over to that oxygen. And again, this is probably going to be the major contributor. So this oxygen is going to carry this positive charge better than the carbon. So carbons are very poor at handling charges. And so sort of a rule of thumb, not like a necessary rule, but a rule of thumb is that major contributors are going to be molecules where the charge is not on the carbon. So when you have the charge on the nitrogen, that, for instance, is going, or on oxygen, those are going to be major contributors rather than having the charge on the carbon. All right, then we have this structure right here, and so I've sort of suggestively put it sort of towards the center of my screen, and we'll see why here in a second. So we have these collapse here, these go up to make that right there, so we have our nitrogen there, double bound to a carbon, that goes down there, 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 up to there. This is still a double bond. We now have the charge on there, and that goes to a CH2 there. So this can collapse down on there. These will go up there, giving us another resonance structure. So I'm going to scroll over here. And so now we have, so this should still have that hydrogen bound to it there. So now we have that bound to the hydrogen. It's double bound to that carbon. That goes down there. this goes down there, and that is a double bond. And then that goes there, up to there. This is a double bond. This is now a single bond, and we have our negative charge right there. And again, with these resonance structures, we'd use these double arrows because it's just as valid to go in the other direction. So you might be given instead this structure in your homework, and then you'd want to sort of collapse that down there, put that up there, so you'd end up back to this one here, then you'd collapse that down there and that back onto the nitrogen and end up at that structure right there. And so like I said, I put this in the center here because it would be just as valid to have this collapse down to that side and then go over here. And so we end up with our N with the H there, but now the double bond is on that side, and we go up like this. This is still a double bond. That is still a double bond right there. And now we have that right there, so the negative charge on that carbon. Again, this is going to be the major contributor because it doesn't have any charges. So I think you'll notice that I made a mistake here. I've been putting this negative charge here, but I've been forgetting to put the positive charge on these nitrogens. And so that rule that I said where the overall charge has to remain the same is sort of a good check you can use for yourself that you are doing things correctly. And your organic chemistry professor is probably going to be very strict on making sure you keep track of these charges. And so the fact that I went from this neutral thing to something that had just a negative charge told me that I was forgetting to put a charge somewhere, and that was on that nitrogen there, which should have that positive charge. But anyway, getting back to what I was talking about, this is going to be our major contributor because we can see, for one, it doesn't have any charges on carbons, but two, it just doesn't have any charges on any atoms, and so that's going to be the major contributor there. And what we will find out later on in this course is that the major contributor to a resonance structure is going to tell us sort of what atom on our molecule is going to be the most reactive. And so on this one, since this nitrogen has that lone pair, that nitrogen will be sort of the most reactive part of that molecule. But anyway, those were just some exercises for resonance structures. So I would encourage you to sort of go through these yourself and look for other exercises in your textbook or online or things like that for these resonance structures, because these resonance structures, the way that we draw things like this, are sort of two prerequisites for being able to even understand how to do organic chemistry. These are things that are going to be assumed that you know how to do sort of going forward from this point. But anyway, I've been kind of rambling on. I hope you found this video helpful, and I will see you in the next one.